This wasn't seen from Earth. It was seen from the sun's side. While telescopes on our planet struggled with glare, atmosphere, and geometry, one spacecraft was already where none of them could be. Deep inside the inner solar system, close enough to the sun that looking away was never an option. For weeks, Earth-based observatories had gaps, blind windows, moments where 3i Atlas slipped too close to the sun's light to be tracked cleanly. That wasn't a failure of technology. It was a limit of position. You cannot see through glare when you're standing directly behind it. But Parker's solar probe was not behind the glare. It was living inside it. Designed to survive heat and radiation that would destroy normal instruments, Parker's cameras kept watching while others had to pause. Not sharper, not prettier, just continuous. Frame after frame, taken from a place no telescope on Earth could occupy. And that matters more than it sounds. Because when you stop thinking about power and start thinking about perspective, you realize something uncomfortable. Sometimes the difference between nothing unusual and something doesn't fit is simply where you're standing. From Earth, 3i Atlas looked intermittent, fragmented by gaps in observation. From Parker's side of the sun, it became a continuous story instead of snapshots. And once you have continuity, patterns begin to emerge. That difference in position didn't just improve the view, it changed what questions could even be asked. This probe was built for conditions no telescope can survive. Parker's solar probe was never designed to make pretty pictures for the public. It was built to do one thing: operate where light, heat, and radiation overwhelm almost every other instrument we've ever launched. While traditional telescopes must turn away from the sun to protect their optics, Parker was designed to move closer to it than any spacecraft in history and keep working. That difference matters because of one specific system on board: the WISPAR cameras. They are not high resolution in the cinematic sense. They are wide-field, raw, and brutally honest. They don't smooth, beautify, or filter reality into something comfortable. They record what's there, even when it's faint, distorted, or partially lost in solar noise. WISPAR was built to image the space around the sun itself, the dust, plasma, and faint structures that exist where glare usually wins. It sees motion first and detail second. That makes it uniquely suited to tracking objects that pass through regions Earth-based telescopes struggle with most. So when 3i Atlas moved into that harsh inner zone, the place where ground observatories had to pause or interpolate, Parker did not blink. It did not wait for better angles. It did not need darkness or distance. It kept watching. That means the data Parker captured isn't a highlight reel. It's a sequence, a progression, a record of how 3i Atlas behaved when conditions were at their most extreme and least forgiving. And that continuity is exactly what makes these observations different from everything that came before. From Earth, the story kept going dark. At the most critical moments, 3i Atlas slipped into the one place ground-based telescopes cannot follow. Too close to the sunday, too much glare, too much scattered light. From our position, the object didn't disappear, our ability to see it did. Observations paused, models filled the gaps, and everyone waited for it to reemerge on the other side. But Parker's solar probe was never in that blind spot. From its position inside the glare, Parker watched the environment continuously. While Earth-based instruments had to step back, Parker stayed aligned with the region where 3i Atlas was moving. There was no interruption, no blackout window, no need to guess what happened in between. That difference changes the kind of data you get. Earth-based images tend to be snapshots, isolated moments stitched together after the fact. Parker's view is closer to a timeline. Motion, orientation, and subtle changes don't have to be inferred. They unfold frame by frame. This matters because some of the most important behavior doesn't happen when an object is cleanly visible. It happens during transitions, when lighting angles shift, when solar wind conditions intensify, when material interactions evolve instead of spike. Those are the moments Earth often misses. From Parker's perspective, 3i Atlas didn't blink in and out of view. It stayed present against the background of the inner solar system. That continuity allows scientists to compare what the object was doing before, during, and after the harshest conditions without relying on assumptions. And that's the quiet problem with relying only on clarity. A sharp image tells you what something looks like. An unbroken sequence tells you what it's doing. These were not the kind of images people expect. No dramatic colors, no clean edges, no perfectly framed comet glowing against a black sky. What Parker's solar probe captured through its whisper cameras looked rough, uneven, almost unfinished, and that is exactly why the data matters. Whisper is not designed to make pretty pictures. It is built to survive intense sunlight and record faint structures moving through a blinding environment. The images come out raw, grainy, sometimes counterintuitive, but they preserve motion and context that polished telescope images often lose. Most space images go through layers of processing. Noise is removed, contrast is adjusted, features are enhanced to make them easier to interpret visually. Whisper does far less of that. What you see is closer to what the instrument actually measured, even if it looks strange at first glance. That messiness is a feature, not a flaw. In raw Whisper frames, brightness shifts are not smoothed away, subtle streaks are not erased. Changes in structure from one frame to the next remain visible instead of being averaged out. For something moving near the sun, that matters more than aesthetic clarity. Scientists looking at these sequences were not asking, "Does this look good?" They were asking, "Does this change?" And because Parker watched continuously, those changes could be tracked over time. Small deviations, slight reorientations, features that appeared, faded, and reappeared as 3I Atlas moved through different solar conditions. From Earth, those details blur together. From Parker's raw perspective, they stay separated, which is why these images raised eyebrows inside the data teams. Not because they were dramatic, but because they refused to settle into a single, simple interpretation. And in those raw frames, something stood out. The surprise was not how bright 3I Atlas looked. It was how the material around it behaved. From Earth, most observations collapse motion into a single frame. You get a snapshot tail here, coma there, and the rest is inferred. Parker's solar probe changed that. Its position allowed scientists to watch how dust and plasma actually moved as the object passed through intense solar conditions, frame by frame, without the usual observational gaps. And when motion becomes the focus, assumptions start to wobble. Material near 3I Atlas did not simply stream away in smooth, predictable arcs. Some structures appeared to stretch, then compress. Others drifted sideways relative to the expected flow of solar wind. Instead of a single dominant direction, there were competing motions layered on top of each other, subtle but persistent. This matters because near the sun, behavior should simplify, not complicate. Solar radiation pressure and the solar wind usually overwhelm everything else. They dominate the environment. They straighten things out. Most comets look more orderly the closer they get to that regime. But Parker's continuous view suggested something less tidy. The movement around 3I Atlas seemed responsive rather than purely passive. Not dramatic, not explosive, just slightly off script. Features that should have been smeared out by the solar environment held together longer than expected. Others shifted direction without a clear external trigger. Scientists were careful not to overinterpret this. Motion near the sun is complex. Plasma environments are turbulent. Projection effects still matter. But when you can track the same structures across multiple frames, from a stable vantage point, patterns begin to stand out, even if they are small. And those patterns did not line up neatly with the simplest models. Nothing here screams conclusion. But it does force a pause. Because when behavior, not brightness, becomes the anomaly, the question changes from, what are we seeing, to something more unsettling. Why is it moving like that? This is how anomalies are tested. Not with headlines, not with speculation, but by stacking perspectives until coincidence runs out of room. What makes the Parker Solar Probe data matter is not that it replaces Earth-based observations, it completes them. Telescopes near Earth see 3I Atlas from one angle through glare, gaps, and geometry that can distort interpretation. Parker sees it from somewhere else entirely, inside the solar environment those same telescopes are trying to peer through. That difference is everything. When Parker's Whisper data is compared with observations from Earth, from Hubble, and from other spacecraft, scientists can begin ruling things out. If a feature appears only from one viewpoint, it may be geometry. If it persists across multiple perspectives, it becomes physical. Parker helps separate illusion from structure. This is especially important for dust and plasma behavior. Near the sun, small changes in viewing angle can flip apparent direction, brightness, or shape. Parker's proximity allows researchers to model how solar, wind, radiation pressure, and charged particles are interacting with material around 3I Atlas in real time, not just in retrospect, and that feeds directly into the models. Every frame Parker collected becomes a constraint. It tightens estimates of particle size. It refines how fast material is moving. It limits which explanations remain plausible and which quietly fail. This is not about proving something extraordinary. It is about eliminating what does not work. That is why institutions pay attention. When multiple viewpoints begin telling the same story, even a subtle one, confidence shifts, not toward conclusions, but toward clarity. And clarity is what turns an odd observation into a real scientific question. We tend to assume that better images lead to better answers, sharper pixels, cleaner contrast, more detail packed into a single frame. That instinct makes sense, but in this case, it is slightly wrong. What Parker Solar Probe changed was not resolution, it was context. Most of what we think we know about 3I Atlas comes from snapshots taken at specific moments, from a single region of the solar system. Earth-based telescopes watch, then lose sight. They reconnect later and try to infer what happened in between. That gap quietly shapes interpretation more than people realize. Parker removed that gap. By staying inside the system, inside the glare, inside the environment itself, Parker turned time into the variable that mattered most. Instead of asking, what does it look like now, scientists could ask, what stayed consistent while everything else changed? That shift rewrites how the data is read. Features that seem dramatic in isolation often lose importance when tracked continuously. Other details, small motions, slow drifts, subtle changes in structure suddenly become dominant. Parker's value was not showing something shocking. It was showing what did not disappear, what did not flip direction, and what did not behave randomly when conditions intensified. And that rules things out. Illusions caused by changing angles, artifacts from intermittent visibility, interpretations built on missing phases. One by one, those explanations lose ground when an object is observed without interruption. So the real contribution here is restraint. Parker helps narrow the field. It trims away possibilities that once felt reasonable. And in science, what you can confidently discard is often more valuable than what you think you have discovered. Which leads to the most important takeaway for returning viewers. The question is no longer what Parker saw. It is what Parker made impossible to argue anymore. It is tempting to treat every new spacecraft image as a verdict, a reveal, a moment where uncertainty collapses into certainty. But that is not what happened here. Parker Solar Probe did not uncover intent. It did not uncover danger, and it did not uncover anything that rewrites physics overnight. What it uncovered was context. 3I Atlas did not suddenly change its behavior when Parker saw it. The object did not become strange near the Sunday. What changed was our position in the system. For the first time, we were not watching from the outside, squinting through glare and gaps. We were watching from within the environment, shaping the object itself. That matters. From Parker's vantage, features that once felt abrupt appear continuous. Motions that seemed abrupt from Earth become gradual when tracked without interruption. And effects that look dramatic in isolation begin to settle into patterns shaped by geometry, plasma, and solar interaction rather than mystery. This is why the mission matters beyond a single comet. Interstellar objects challenge our assumptions because we rarely see them under consistent conditions. Parker helped fill in those missing pieces. It did not give us answers so much as it removed blind spots, the kind that quietly distort conclusions without anyone noticing. And that is the real lesson here. The sun's own probe did not expose a secret hidden inside 3I Atlas. It exposed how incomplete our view had been all along. That may not sound dramatic, but in science, that is exactly how understanding moves forward, not by surprise, but by clarity.